The heart is the first organ to develop in the growing embryo. But within that developing heart also lies the first rhythm, the first heartbeat. For centuries now, we've been studying this process and trying to understand it better by looking at models, looking at books. But these paint a very static image of the whole process. We only have static pictures. But what if we could look at the process as a movie, now capturing all its ebbs and flows? And this is something that with new technologies, we might just be able to do it. My name is Claudio Cortés, and I'm part of a group of researchers in Oxford that is trying to unravel the mysteries of this first heartbeat. So we are developmental biologists, and we believe it's important to try to see things from other points of view. As part of our research program, we have been collaborating with a computational artist, Andy Lomas, to help decipher how dynamic patterns, rhythm, and form can spontaneously emerge within unsynchronized matter. The outcome can be seen here in this stereo viewer that is providing us with very interesting reflections on how this synchronicity might arise, but also into how the first heartbeat might happen. Hi Andy, how are you?
I'm doing good, thanks Claudio.
So you know that when we've been studying embryonic development, we've mostly been basing our studies on static images. But now that we can look at the processes via movies and see them happening and get the dynamics and the ebbs and flows, we're starting to see some very interesting behaviors there. I think one of the key ones is that really early on in the developing heart, cells are not coordinated. Early on, it seems to be random.
Yeah, absolutely. I think that's one of the really interesting things. I think it's basically, how do we get order emerging from randomness, even if we haven't got any sort of central planning or control mechanisms in the system? I guess that's one of the main things we're trying to explore with the artwork. It's not trying to be an accurate model of heart development. It's trying to look at how, if we've got a really simple model of cells that can influence each other, that can lead to a wide range of really interesting emergent patterns of behavior, some of which seem to remarkably similar to what we're seeing during early stages of embryo development. I guess maybe what's good is to look at some models of how synchronization can spontaneously occur. What we've got here is 3 metronomes, and if we just set these off sort of ticking, they'll just do their own independent thing. But if they're on a board together and we set them up so that they can just rock a little bit from side to side, quite quickly the metronomes can get into synchronization.
Oh, so in the case of cells, even if they were not in sync to start with, if you allow them to affect their neighbors, then they can get in sync.
Yeah, I think absolutely. If when a cell contracts, it can also affect other nearby cells and make those contract as well, that can lead to chain reactions and potentially sustained waves of activity.
Sustained waves of activity. So this is something that we see slightly later in development. So what we're looking at here is a Mexican wave. So if you've ever seen one of those at the stadium, then what you get is that a group of people on the benches will stand up, and then the people immediately to their side will stand up too, and before you know it, you have a wave of people that are standing going all across the stadium. After the wave has started, then the initial, in the case of the Mexican wave people, or in the case of the heart cells that started this wave, are no longer required for the wave to continue traveling. Emergent properties are all around us. The structure of a snowflake, the murmuration of flocking birds, the patterns found in weather, and even traffic jams. From simple rules, dynamic loops can be created, which brings us both the properties of a higher order system, but also often a sense of aesthetic appreciation. So Andy, what do we have here?
So what we're seeing here is a computer simulation where the cells have a potential level, and when that level reaches a certain threshold, the cell contracts. But when it does this, it also affects the other nearby cells by raising their potential levels, which can trigger them to contract too, allowing chain reactions to happen, very much like the Mexican wave. One of the big things is that we know with this simulation that there really isn't any central controller. All the cells are running exactly the same algorithm, so all the patterns we're seeing really emerge from the system without there being almost like a conductor of the orchestra. You can adjust the potential levels of the cells and also how strongly cells affect each other, which allows you to explore, I guess, a wide range of different rhythmic dynamic sort of patterns. But also allows you to explore almost how transitions can happen, how you can get the system moving between one state and another.
Yeah, this is particularly interesting in what we study in heart development, because a lot of transitions happen later in life. For example, after a heart attack, heart will scar and it will conduct contractions in different ways. So there's quite a lot of this that we're interested not just in the context of embryonic development, but also in the context of disease. And I think that we see that the system is more than the sum of its parts. One of the things that your artwork is bringing to the table is allowing us to better understand some of these transitions. What causes heart malformations remains mostly unknown. Today, by studying changes in the growing embryos in real time, we are revealing processes in all their detail. This is particularly important in the heart, where form and function are intricately entwined. It is through thinking outside the box and collaborating with people from other fields that we can continue to unravel the mysteries of the heart, and at the same time get further drawn into its beauty. We are currently redefining and pushing the boundaries of research. We want to truly understand how the heart forms, from the first rhythms from the first heartbeat.